This video is on imaginary and complex number operations. Imaginary numbers are denoted by the letter I. I to the power of 1 is defined as the square root of -1. And so we can just write that as I. Now we don't usually leave the square root of -1 or replace I with the square root of -1 in a problem. So the way that you would use this is if you're solving a problem and end up with a negative under the radical, we can use I to simplify the answer. The square root of -4 is equal to the square root of -1 times the square root of 4. -1 times 4 is -4. Well, the square root of -1 is I, and the square root of 4 is 2. And so we'll write our answer as 2I. Notice that I put the 2 in front. This is just something that we've sort of agreed upon, that I2 looks and sounds funny. And just like with variables, we always put the letter after the number. If we square I, that's equivalent to the square root of -1 squared. If you remember, squaring and square root cancel each other, and so we end up with -1. And you may recall from working with imaginary numbers previously that this one gets used an awful lot. I squared is equal to -1 is an important one for you to memorize. I to the third, well, that's I squared times another I. Remember, when we multiply variables, we add exponents. But I squared, we already know, is -1. And so if we multiply -1 times I, we get -I. Well, we can do the same thing for I to the fourth. I to the fourth is I squared times I squared. Add exponents, you get the 4. But I squared, each of them are equal to -1. And when we multiply -1 times -1, we get +1. If you look at these, and you may remember, there's quite a pattern here. I, -1, -I, 1. And this pattern repeats every power of I. So I, -1, -I, 1. I, -1, -I, 1. Those of you that have had me for a teacher before remember this little song that we sing to recall the pattern that I follows. Let's look at an example. I to the power of 38. Since this pattern repeats every 4 powers of I, we can divide 38 by 4. We're not really interested in how many times it divides in evenly. We're interested in the remainder, because I to the 38, this is I to the first, to the second, to the third, to the fourth. I can go back to the beginning, I to the 5th, I to the 6th, I to the 7th, I to the 8th, and you could keep doing that and count up to 38, and wherever you land, that's what I to the 38th power is equal to. But rather than do that an awful lot of times, we know that 38 divided by 4 goes in evenly 9 times. That gets me all the way to 36. I'll have a remainder of 2, and that's the important part. That remainder of 2 tells me that I to the 38 is equal to the second term in the pattern, which is I squared, which is -1. So I to the 38 is equal to -1. Divide by 4 and look for the remainder, and you only have to count that far through the pattern for I. Let's review how to perform operations with complex numbers, and then we'll do a few examples. The examples will come from the worksheet you'll see in class, so I suggest that you copy them when we get there, and you'll be able to transfer them onto your paper in class. The rules for adding and subtracting complex numbers are the same as with polynomials. That means that you combine like terms, just like you would with polynomials. The rules for multiplication are also the same as polynomials. You still distribute. You still use either the arrows or the box to multiply complex numbers, but you do have to simplify. You have to replace all powers of I with the simplified answer. The rules for division are to first multiply the numerator and the denominator by what's called the conjugate. And we'll review what a conjugate is for a complex number. Once we multiply the numerator and denominator by the conjugate, then we have to simplify again. Let's look at some examples. All right, if you look at number 1 with me, we can treat these problems the same way we would as if I was just any other variable. The only thing that we have to do in the end, if necessary, is to simplify any powers of I greater than I to the first power. In the case of number 1, we have like terms, which you still have to have, just like polynomials. And since they're like terms, we combine what's in front of them, and we have a negative 3i as our solution. If you look down further at, say, number 5, you'll notice that we have a subtraction problem. And just like with polynomials, the rules are the same. Instead of subtracting an expression, we change it to adding the opposite of everything in the parentheses. So this becomes positive 3 plus 8i. And now that's gone. Now we can combine like terms. I have a negative 6 plus 3, that's negative 3. I have a positive 8i plus 8i again, and that's plus 16i. Remember that standard form for a complex number is a plus b I. The I part, the imaginary part of a complex number, should always come at the end. Let's go down to multiplication and review what to do there. If we look at number 7 together, 5i times 6i. Be careful, this is all multiplication, and that means that the 5 is being multiplied by the 6. Notice the difference that you don't have to distribute here. We only distribute when there's adding or subtracting involved in the parentheses. In this case, there's not. So 5 gets multiplied by 6, and I gets multiplied by I. But here we have I squared. And your answer should never have any power of I greater than 1. Remember, I squared is negative 1, which makes this negative 30. Don't forget when you look at problems like 11 and 12 that you follow the same rules as for polynomials, and either do the arrows or the box to distribute everything in the first set of parentheses to everything in the second set of parentheses. The only difference with I is that you'll have to simplify any powers greater than 1. Let's quickly remind you what it means to be a complex conjugate. A complex conjugate means that you're going to change the sign of the imaginary part of the complex number only. So when we look at this expression, change the imaginary part only. Standard form puts the I part last. So this would be negative 8 plus I in standard form. The conjugate changes the sign of only the imaginary part, which means the conjugate is -8 minus I. Be careful only to change the imaginary part of the expression, and sometimes it's confusing if it's not in standard form for a complex number. So if it's not, you may want to switch it around first. We use complex conjugates to simplify problems like number 18. When we do so, we find the conjugate of the denominator, which would be 4 minus I, change the sign of only the imaginary part. And since we're going to multiply this to the denominator, we also have to multiply it to the numerator. I want you to think about why we're allowed to do this. When we multiply now 4I times the quantity 4 minus I, we distribute 4I times 4, 16I. 4I times -I is -4I squared. We'll take care of that. I hope it jumps out at you. I squared can't stay in our answer. When you multiply the bottom using the box or the arrows, you will find that the middle terms cancel, and that is because we multiplied by the complex conjugate. We did it on purpose so that that would happen. We end up with 16 minus I squared, and again, that I squared comes in handy. Remember that I squared is equal to -1. Put it in parentheses if you're going to cross out and replace that way, because it's important that you don't lose the negative or think that you're subtracting 1. In some cases it's possible, but more often than not, you're multiplying that. The numerator is 16I. -4 times -1 is +4. And in the denominator, we get 16 minus -1. That's 16 plus +1, which is 17. And this is where it can get a little tricky. I highly suggest that you write out your steps, and we'll practice the rest of these in class. There's no reason to copy any others other than the ones that I've done as examples. So you may want to pause the video and go back and get those written down if you haven't already.